Um, we're going to spend a bit more time today on the instrument. I didn't spend a lot of time on the instrumentation for GC, not because it's not important, obviously, but because the instrumentation is really a lot simpler and it's a lot easier to maintain. And there are not so many great differences between brand A GCs and brand B GCs. They're just not that different fundamentally. But LCs, there's a wide range in properties, and you need to be familiar with them so that you can pick out the appropriate instrument when you have some money to spend and to solve a problem. You need to know the important characteristics of the LC and how it works. So we're going to return to where we left off last time in terms of instrumentation. And then the rest of today we'll talk about the different kinds of particles used in HPLC. And we're going to spend a lot of time talking about the surface chemistry, especially of silica. Probably 90% of all HPLC uses silica. The rest of HPLC is all sorts of things: alumina, synthetic organic polymers, biopolymers, all sorts of things. But the vast preponderance of HPLC work is done on silica and chemically modified silica surfaces. So we'll spend a good bit of time on that. And then we'll talk about the different kinds of HPLC: normal phase, reverse phase, ion exchange, and sort of a big picture of what they are and what they're used for. And then later on we'll get into the details of how they work. Okay, so back to our buddy, the reciprocating piston pump. This is the dominant kind of pump used in HPLC. There's obviously all sorts of pumping systems. I'm sure at some point or other you've seen a peristaltic pump. Peristaltic pumps are useless in HPLC. They just can't generate enough pressure. But reciprocating pumps do. I described how they work the other day. They're relatively inexpensive, as I said, but if you have to think of $5,000 as being inexpensive. You can get to very high pressures with these pumps. The downside of a reciprocating piston pump is they generate pressure pulses because the pump has to go like this. And if the pump motion were the same in both directions, what you would see in terms of a pressure drop would be something like that. And then during the backstroke, you'd be essentially at zero pressure, and then you'd get another one like that. And that's bad news. If you had a pump that emptied slow and moved back like that, it'd look more like that, which is still really ugly. And pressure pulses are very, very bad because they generate signals at your detector. I don't care if it's a refractive index detector, a UV visible absorbance detector, an electrochemical detector, a mass spec detector. They're going to respond to these pressure pulses. So one of the ways to get around these pressure pulses or minimize them is to use what we call a pulse dampener that makes use of the compressibility of the fluid that you're pumping or of another fluid. I'll show you how one of these works in a minute. But the real answer to this problem is to use a pair of pumps that are 180 degrees out of phase. and you overlap those pressure cycles to essentially create an interference pattern that wipes out that pressure dip. Now you can never make that perfect, so they will follow up the pair of pumps with a pulse dampener. And you can really do a good job of getting those pressure pulses even at 400 bar. If you do it right, your pressure pulse may only be 3, 4, maybe 5 bar at a 400 bar. That's less than a 1% pressure going up and down, and that's much more tolerable. Here's the pulse dampener system, and usually they also build a pressure sensor in there. You want to be monitoring your pressure on your system. If you see changes in day-to-day, the pressure, something's going on. The pressure pattern should be very reproducible from day to day. But in any case, you have an inlet and an outlet, and up here is some kind of compressible fluid like an oil. And there's a diaphragm here, and the fluid goes into the diaphragm, and the diaphragm under the pressure expands a little bit, and the oil compresses a little bit and resists. And then that pressure, that compression of that fluid is stored so that when the pressure attempts to drop, the fluid expands against that drop and maintains a constant flow rate. It's really rather like a capacitor in an electrical circuit, where the capacitor will store charge. This is storing fluid, and when the pressure attempts to drop, the fluid expands against that drop and maintains a constant current, a constant flow. And that's what happens in a capacitor. Of course, this system here has volume. Your sample doesn't go through it. This is all taking place before you inject your sample. But it has volume. And if you go to change the fluid in the system, it takes some volume to flush out what was there before. So this is part of what we call the dwell volume when we do gradient dilution. And we'll get into gradient dilution in a little bit. Another kind of pump is a syringe pump. Some people simply call it a screw pump. Just imagine a big syringe attached to a plunger on a screw. The motor turns the screw advances and pushes the fluid out of the syringe. These were actually really popular at the beginning days of HPLC, and they had some of these things that had a liter, a syringe that would store a liter. The problem with them was that it takes a long time to get that liter fully compressed. It could take minutes to get that compressed, and so the flow rate would gradually increase until you got to a constant flow situation. It is highly free of pulses. They can cover a very wide range in flow rates. They're relatively inexpensive. The flow rates are really precise once they're up, once the fluid is completely compressed. But the problem is it's a finite volume. Nobody made a 10-liter syringe that would go to 5,000 psi. Frequently, when you've got an assay running 24 hours a day, people will be making up multiple liters of mobile phase. You don't want to have to change the mobile phase during a run. So that was definitely a limit of the system. And physically, they're pretty big. I mean, they have to be as big as the volume of fluid you want to work with. Another device that was used extensively, but I don't think anybody's using it anymore, is a thing called a diaphragm pump. And so basically it's a piston type of device, but the piston compresses a fluid that's in a sealed chamber here, okay, here, and that oil behind the membrane is being compressed, and it pushes against the fluid that you're pumping. The beauty of it is it's got lower pressure pulses because of the compliance of the fluid, of the oil that's behind the membrane. There's no contact between any moving parts other than the surface of the membrane and the fluid you're pumping. So they were chemically pretty inert. There's no seals like in a conventional piston pump. The pressures were limited by how strong the diaphragms could be made, and they could go to fairly high flow rates. This was the workhorse type of pumping system in the old Hewlett-Packard 1090, and there must be 20 or 30,000 of these pumping systems around the U.S. still to this day. They were extremely reliable types of systems and fairly easy to maintain. Yes, Ryan?
For the syringe pumps, would those be used for capillary work?
They actually are used for capillary work still today, because you can go to you can get a small syringe, meaning a couple of milliliters, and a capillary, flow rate might be 10 microliters per minute. If you had a 10 ml syringe, that's a pretty long time. And they do deliver at a pretty constant flow rate. So they're still used for capillary LC. A lot. They're not the only approach, but a lot. Okay. One of the dirty secrets of HPLC is that you gotta get the gases that are dissolved in your mobile phase out of the mobile phase. Especially if you're doing gradient dilution work. And the reason is the following. Let's suppose we're mixing water and methanol in a gradient dilution HPLC run. The solubility of atmospheric gases, oxygen, nitrogen predominantly, obviously, in water is much less than the solubility of gases, atmospheric gases in methanol. Gases are relatively low polarity substances. They prefer to dissolve in organic than in water. Now, so you got a methanol with a lot of gas in it, water, not much gas, but when you mix the water with the methanol, the solubility of the gases in the mixture is now lower, and so they outgas, which means they form bubbles. And the bubbles can hang up in the pumping system. And once you get a bubble in the pump simply compresses and decompresses the bubble. The bubble keeps getting bigger, smaller, bigger, smaller. No fluid, or not none, but less fluid than you anticipate comes out of the pump, and you've lost control of your flow rate. That's one evil. However, because that fluid upstream of the column is under pressure, the bubbles frequently stay in the liquid. They don't come out. The liquid is supersaturated with the gas, but because it's under high pressure, the gas can't get out. But when you get to the end of the column, where there's a low pressure, then the bubble forms, and it goes through your detector, and it drives your detector absolutely bat nuts, and you get horrible baseline noise. So there's all kinds of mechanisms that have been developed to get the gases out of the fluid. Simply pulling a vacuum on it to begin with was an early way to go. Another way to go was to sparge the gas, the oxygen and the nitrogen out of your solvent with helium. Helium has a very, very low solubility in almost anything. It's not a very polarizable substance, and so you sparge your mobile phases with helium. It takes out an awful lot of your gases, and they were reduced to a level that it didn't matter. But the predominant, and it's probably 90% if not more of what's done today, is what's called an on-line vacuum degasser. So your fluids, let's say again water and methanol, go through a special tubing, usually a polymer, a Teflon. Teflon AF is one of the most popular. Gases can come right through that membrane. They diffuse through it very, very rapidly. It's a well-known property of perfluorinated membranes. And you pull a vacuum on the other side of the tubing, and it's like you're pumping the gas out, and the liquid, water and methanol, acetonitrile, don't go through the tubing. They don't have a very high diffusion coefficient through the polymeric, the Teflon AF tubing. The gases do. So you can get rid of most of the gases. You do not get rid of all of the gases. Usually something like 90% of the gas will be gotten rid of. So this protects the pumps from failing, and it makes your baseline noise a lot better. Ryan, did you have a question?
Yes, and then I forgot it. Oh, so they used helium to get the gases out of the mobile phase, so then they had helium still in the
Yes,
mobile
but the
phase?
helium has an extremely low solubility. So there just wasn't much of it, so it didn't bother anything. Yeah. If you were to use argon, argon has the solubility on the order of oxygen and nitrogen, if not higher. So it's not the inertness of the gas. You could use hydrogen if you wanted to, if you didn't mind filling your room up with hydrogen. Okay. So enough about pumps. Performance tests. To me, this is the minimum. This is not all that good. But what they're saying is that you want your flow rate to be constant to within 1%, or about 20 microliters per minute. If you were going at about 2 milliliters a minute, which is a typical flow rate for HPLC. And the way you do this, the way you measure this, is pump water, measure the amount of water over a period of time, and then you weigh. Don't bother measuring the volume. That's ridiculous. You graduated cylinders, no good. Forget about it. You got to weigh the water if you're looking for 1% reproducibility. Then there are things we do to test the gradient when we deliberately change the mobile phase composition. We want the pumping system to accurately do what we want. So the way we check it out is we put water, and if it's a binary gradient, we put water on one side, and we put water with a trace amount of acetone on the other side. Acetone is a very nice UV signal. And of course, water mixes nicely with water. There's no problem. If you try and mix water with isopropanol, big differences in viscosities, densities, surface tensions. They don't mix. They're completely miscible, but the rate at which they mix together is a little slower than water mixes with water. And you run a linear gradient. And this is what, for instance, a 1290 pumping system is capable of. You can see that the blue trace, which is actually just measuring the increasing amount of acetone as you do a gradient from pure water to the water plus a whiff of acetone. It's a nice straight line. You get to the end of the gradient and you go back to pure water, so you tell it, okay, go back as fast as you can. It does not return instantly because you've got to flush out the parts of the pumping system that were already filled with the water acetone mixture. So this is what we call the gradient dwell or the gradient flush out. Obviously, the higher the flow rate, the quicker you can flush it out. The really important number is the gradient dwell volume, because that's pretty much independent of flow rate. And if you're buying a gradient system, you're strongly advised to buy one with a rather small gradient dwell volume. It will perform quicker and somewhat more reproducibly. And this time can actually be a significant fraction of your analysis time if you're doing fast analyses. Especially if you're working at a low flow rate, which takes it longer to flush that volume out. There's another important way to check the accuracy of the gradient, and that's to do a series of gradient steps. And again, we use water with acetone in it. And so this is 100% water here, 100% water, no acetone. Notice the baseline. Each of these is 10 milliabsorbance units. So the noise here might be 5 or 10 microabsorbance units, and that's due to the residual pressure pulses more than anything else. Now, this is 10% of solvent B with a trace of acetone in it, mixing with 90% of solvent A, and you see a much more wiggle here. That's due to the mixing not being bang on. Remember, we've got water, and we've got water with acetone, and we're getting pulses of those being mixed together, and they have to be blended, and you're seeing the residual unmixedness, the heterogeneity in the system. Up here, it's a 5% step, and what you do is you measure to make sure that this is in fact 10% of the total change when you go all the way up to the final. And you make sure that this is accurately 5% of the total change when you go all the way up to the final. And if it were, say, 3%, your pumping system is not doing a very good job. And you would not get that kind of trace if you did a linear gradient. It would probably curve up and then curve over towards the end. You don't want that. Yeah.
So you use the accuracy test as a measure of both the mixing efficiency and the pump.
Yeah. That the two pumps are pumping precisely the fractions of the total that you want. Okay. One of the most important tests you can do is check the reproducibility of the retention time. It really tests the whole system, especially in gradient dilution. The reproducibility of the gradient time is a test of everything. If the column temperature is fluctuating, then the retention time is going to fluctuate, because the retention time is a thermodynamic property, and it depends upon temperature, depends on the enthalpy of the transfer from one phase to the other. It also checks the pumping system flow precision. And the other thing it's a test of is your detector sampling frequency. Let's suppose you only take a signal every 1/10 of a second. You can't measure retention more precisely than a 1/10 of a second. Now, a good detector these days is sampling at 20, 40, or 80 hertz. Okay, now if you get reproducibility to 1/80th of a second, you've got a really, really reproducible system. Reproducibility under isocratic conditions is easier to achieve than reproducibility under gradient conditions, especially if you make what we call a hand-mixed mobile phase, where if you want to do 50-50 water acetonitrile, you weigh up the water, you weigh up the acetonitrile, you combine them together, you mix them together, and you pump them, as opposed to running in a binary system and having one pump deliver 50% and the other 50%. If there's any imprecision in the flow rates, that's going to show up. But if you hand mix, you're going to get more reproducible results. So that's the way to see if your pumping system is really reproducible, is hand mixed versus machine mixed mobile phase. Here's a set of specifications of an Agilent 1290 pump. I'm not saying this is the best pump going. They just had a nice set of specifications that I could copy. But it is a dual piston pumping system. It controls the flow rate to 0.001 milliliter per minute, and it goes up to 5 milliliters per minute in 0.001 steps. The flow precision is 0.07% relative standard deviation, or it's 0.005 minutes standard deviation, whichever is bigger. So in other words, you can't beat 0.005 minutes no matter what you do. That's quite acceptable to them. Now I'm here to tell you we have seen systems that, including this system, that are much more reproducible than plus or minus 0.005 minutes on a retention time, even under gradient elution conditions. This is a somewhat generous specification to make sure the system always passes muster. But if it's outside of this, there's definitely something wrong. It may not be the pump, it could be the temperature control. Flow accuracy is 1% or 10 microliters per minute, whichever is greater. I believe it's better than that, in fact. Operating pressure goes from 50 bar to 1200 bar at 2 mils a minute, maximum flow rate, or 50 to 800 bar at 5 mLs per minute. In other words, if you want to go fast, you can't go to as high a pressure. That's life. Pressure pulses less than 1% or less than 5 bar, whichever is greater. Certainly have seen it better than that. Compressibility correction factor. So you got a liquid and you're putting 400 or 1200 bar on it. The liquid compresses. Not a lot. Typically you're only talking 1 or 2% compression. But the problem is that different liquids have different compressibilities. And so if you're trying to make a gradient, you're going to get a nonlinear gradient if one fluid compresses more than the other. So what they do is they have little computer algorithms built into the pumping systems, and you have to tell it what is the solvent in pump A and what is the solvent in pump B. And it has a little table in its little semiconductor brain, and it says, oh, okay, yeah, so if the pressure is this, then the volume compression is this, so I'll pump this one a little faster so that the total flow rate is what you want it to be. This is pretty important, and it also has an impact on the pressure pulses. pH range of the instrument, 1 to 12.5. but it really depends upon what is setting the low pH. It's a really bad idea to use any acid that specifically attacks stainless steel. Hydrochloric acid is an absolute no-no. At these, I mean, maybe pH 2 is okay, but pH 1, no. On the other hand, we have put 1 molar nitric acid through stainless steel pumping systems. If the polymer says you can do it, there are polymers in contact with the fluids, you can put nitric acid through and it does a nice job of cleaning things up by oxidizing the bejesus out of them. Okay, but don't do that with hydrochloric acid, ever. And there's other interesting specs here, but I think we've covered the really important ones. You gotta know what your instrument is capable of. Don't use an instrument unless you know what it's supposed to do. All right, so we're done with the pumping system. We're gonna come back to hardware later when we get into detectors. That's another story. Okay, so particles. The most common particle used is silica, SiO2. Unfortunately, the interface between a piece of silica and a solvent is not SiO2. At the surface of all silica, there's silica. The surface is not SiO2, the surface is loaded with stuff like that. Silica surfaces that are heated to 800 degrees centigrade, they're silica. There's no OH groups. Very few OH groups. It's not right to say none. But if that is contacted with water, it becomes the SiOH, excuse me, the SiO-Si. These rings open and they become OH groups, which are vastly more polar than SiO2. And we'll get more into this in a little bit. Other common particles are alumina, zirconia, titania. Pretty inert stuff. And then synthetic organic polymers like polystyrene. Except we're talking porous polystyrene. And the polystyrene is very, very, very highly cross-linked. Because if you don't cross-link it and you apply 4,000 or 5,000 psi to it, the polymer scrunches down. You don't want that. In low-pressure liquid chromatography, there's an awful lot of use of biopolymers like cellulose and agarose, cephirose, dextran. They cannot handle high pressure. You take something like cellulose or agarose, which are extremely hydrated gels. They're sort of like, you know, watermelon. You squeeze it and the water comes out. They can't take much in the way of pressure. The beauty of them biopolymers is they're compatible with biomolecules. They don't denature. But that's not HPLC, that's LC. But that's still LC, and we're going to talk about it. Okay, so as I said, the vast majority of HPLC is done with silica. There's a number of different ways of making silica particles that are nice, round particles. One fairly simple way is by spray drying. So you take a colloid in aqueous suspension or in organic suspension, and you push it through a nozzle, very narrow nozzle. The narrowness of the nozzle and the flow rate of the gases around the nozzle are going to control the size of the particles that the colloids form. And spray drying is always done with heating, so you're blowing hot gases, nebulizing. It's a lot like the processes going on in a flame atomic absorption system. You nebulize the solution containing the colloid. The colloid particles form aggregates in the hot gas, and they form particles. The problem is the particles are not all exactly the same size. If you control the spray drying really well, you can get reasonably monodispersed particles, but normally not good enough for HPLC purposes, so you have to size the particles. You got to go through an additional step. So you make the particles, but then you size them to the size you want. 3 microns, 5 microns, 10 microns. Of course, you don't get exactly 3, 5, and 10. You get 3 plus or minus a half. You get 5 plus or minus maybe 0.8. You get 10 plus or minus 1 micron. There's always some polydispersity to the particle size. Another way to do it is what's called oil emulsion, where you have your colloid typically in water, and then you put an oil around it, and the oil, something like peanut oil. Water has a slight solubility in peanut oil. You heat this up quite hot, and you stir it really, really fast. And the water goes into the hot oil and vaporizes out of the hot oil, so the colloid gets more and more concentrated, and the particles start to get so concentrated they bump into one another and they aggregate. And the surface tension of the water makes them into beautiful, beautiful round spheres. They're not monodispersed, and there's a fair amount of particle sizing that has to be done. A third method, which is not used all that much, but it's quite pretty, is called polymer-induced colloid aggregation, which actually makes very, very highly monodispersed particles. I won't go through the details of this process. It's pretty complicated. And then the final way it's done is to start not with a colloid anymore, but with a soluble material like a tetraalkoxysilane. And you throw that into either water or a organic solvent, and you add acid. And that causes the hydrolysis of the tetraalkoxysilane, and you start forming SiO2s, and the SiO2s all stick together. Yes?
If the polymer-induced colloid aggregation makes such well monodispersed particles, why isn't it used more often? Is it because it's so complex?
The yield is terrible. You may only get 5 or 10% of all of the colloid that you put in forming these particles, number one. Number two, you don't know the details, and you actually have to wind up burning out the polymer. And some of the particles, if you don't do it just right, the particles fall apart. So it's a tricky, touchy process. It is used, and I won't tell you who, but there are a number of the major manufacturers that make all their particles that way. But they have it protected both with patents and trade secrets, and they'd have to kill you if they told you how exactly they do it. The downside of this is when you're done, you have to grind the silica up. And apparently there are ways of grinding it into spheres, but they're very polydispersed, and there's an awful lot of particle sizing that goes on. But the junk silica that organic chemists use, and some of my good friends are organic chemists, and I tell them it's junk. This is how it's made. This is the cheapest way to make silica. but not HPLC silica. Okay. These happen to be two zirconia particles made by the polymer-induced color degradation process. These were not hand-selected to be identical in size. This is what comes out. There's no sizing involved after these are made. It's really a beautiful process. I'll be done in a second. The last material I wanted to mention are the monolithic silica rods. I'm telling you who makes it because they're the only company who makes a monolithic silica rod, and that's Merck. They've got it completely tied up in patents. We talked about these before. What's inside your stainless steel tube is a single piece of silica, monolith, a single rock of silica where it's all connected and the small particles are connected to other small particles. The idea is it has a low pressure drop and you can go fast. There's only one store. You only got one shop to go to. And they don't make very many different chemically treated silicas with different flavors on the surface. Whereas there are something like 650 different reverse phases that you can buy from all the manufacturers put together. There's like 6 or 7 flavors of this stuff that you can buy. So if you go this route, you better love C18 or C8 coatings on your silica and not much else. But there are definitely good things about these. The patent will wear out eventually and other people will enter the business. And you do have to make a decision. Am I going to use a monolith or am I going to use a conventional packed bed at some point when you buy a column? Yes?
How do packed beds and monoliths compare for degradation over time?
I don't think there's a big difference between them. We'll talk about the stability of the particles pretty soon, but where they may differ is the following, Ryan. One of the causes of column death is junk, what you inject. And these have bigger spaces between the particles, between the pores. You know, these holes are gigantic compared to the space in a packed bed. So these don't tend to plug up as much. On the other hand, if you're doing things right, you should have a guard column in there. And the guard column is what should plug up, and you throw it away, and you keep your analytical column. So it's not that big of an advantage. Okay, we're over, but we're done with this aspect of particles. Next week is spring break.